Our next concept we're going to be taking a look at is something known as chemical equilibrium. Now, chemical equilibrium is for reactions that can occur in both directions. A reaction can run forward and in the reverse direction. Many reactions can only run in one way. For example, the combustion of methane is an example of a reaction that can run in only one direction. This reaction is irreversible. Once combusted, the methane is turned into carbon dioxide and water. This reaction cannot run in the reverse direction to return to methane and oxygen. This would be an example of a one-way or irreversible chemical reaction. An example of a two-way or equilibrium chemical reaction would be both the decomposition of carbonic acid that turns into carbon dioxide gas plus water, in that this reaction can proceed in the forward direction where the carbonic acid is decomposing into carbon dioxide and water, or the reaction can proceed in the reverse direction. If we were to take carbon dioxide and water and bubble the carbon dioxide through the water, we would make a solution of carbonic acid. So this would be a reaction that can run in both directions. The carbonic acid can turn into carbon dioxide and water, or if we took carbon dioxide and water and mixed them, they could turn into carbonic acid. A reversible reaction, also something that could establish chemical equilibrium. And when a system actually reaches chemical equilibrium, one thing needs to be true, and that is that the rate of the reaction going in the forward direction has to become equal to the rate of the reaction in the reverse or backward direction. When this occurs, the concentrations of the chemicals involved in the reaction now remain constant. Let's use this reaction as an example for an equilibrium. Just generically, we have chemicals A and B are going to react and turn into C and D. Initially, we take chemical A, pour it into a container, we add to it chemical B. At this point in time, all we have in the container are chemicals A and B, and their concentrations are both fairly high because the reaction is just beginning to occur. So initially, because the concentration of A and B are high, the reaction is proceeding mainly in the forward direction. But as the reaction proceeds, we start to form a little bit of C and D as A and B begin to turn into product. What this does, the concentration of A starts to go down, the concentration of B starts to go down. Simultaneously, the concentration of C begins to increase and D is also increasing. And this affects the rate of the reaction. As A and B decrease, the rate of the reaction in the forward direction becomes a little bit lesser. As C and D build up, the rate of the reaction in the reverse direction starts to increase. Eventually, we reach a point where the concentration of A and B have dropped sufficiently and C and D have increased sufficiently so that the rate of the reaction in the forward direction and the rate of the reaction in the reverse direction become equal to one another. When this happens, the reaction is known to be at a state of chemical equilibrium. When this occurs, the rate in the forward direction being equal to the rate in the reverse direction, the system is said to be at equilibrium. When this occurs, the concentration of the chemicals are now remaining constant. So at equilibrium, the concentrations of the chemicals involved remain constant. They're unchanging because the rate at which reactant is turning into product is the same as the rate at which product is turning back into reactant. Now, all equilibrium reactions have associated with them something known as the equilibrium constant. The equilibrium constant is essentially a ratio of the concentrations of the products to the concentrations of the reactants when the system is at equilibrium. What the KEQ or equilibrium constant tells us is how much product is present or how much reactant is present when something reaches equilibrium. The setup for KEQ is fairly standard. It's a ratio. It's our products, in this case C and D, divided by the reactants A and B. The coefficient in the balanced equation, the A here, if that were a number, becomes an exponent outside the concentration of reactant A, or in this case the D, whatever the coefficient is for chemical D becomes an exponent outside chemical D as we set up our equilibrium constant expression. Let's use this reaction as an example. The KEQ is going to be products, again, is a ratio of the products at equilibrium to the concentration of the reactants at equilibrium. It's a key thing that it's products over reactants for our equilibrium constant. In our sample reaction, the product is NO2, so we have NO2 inside a bracket divided by the concentration of the reactant N2O4. Because the NO2 has a 2 for our balanced equation, this gets a 2 or a square outside the NO2, and there's a 1 in front here for that, so the exponent would be a 1, and this would be our equilibrium constant expression for this particular equilibrium reaction. Now the exponents being a square or a cube or a single is not something that's just random, but it rather comes from the actual balanced equation. We could rewrite this balanced equation in this fashion, where 2NO2 is the same thing as NO2 plus NO2. If we were to now write our equilibrium constant expression, it would be the concentration of NO2 for one of the chemicals times the concentration of the other chemical, NO2, divided by N2O4. Mathematically, this is the same as writing the reaction as NO2 with a square here, which comes from the 2 in the balanced equation. When setting up an equilibrium constant, another key thing is that materials that occur in the liquid or solid physical state are omitted from the equilibrium constant expression. Reason for this is that liquids and solids have a constant concentration, and therefore their concentration remains the same, whereas aqueous materials, solutions, and gaseous materials, the concentrations can change. They are included. Aqueous and gases are included in equilibrium expressions. Solid and liquids are omitted from equilibrium constant expressions. For example, let's do this reaction that we have. At first glance, this is what our equilibrium constant expression would look like, in that we have the products divided by the reactants. We've included our coefficients from the balance equation as exponents outside the brackets for each chemical. But if we look, the N2CH4O is a solid, consequently that should be eliminated from our equilibrium constant expression, leaving us with an equilibrium constant expression that would look like this for this chemical reaction, where our solid material has been omitted and dropped out of the expression, once again because solids and also liquids have a constant concentration and they are unchanging. Let's try another couple equilibrium constant expressions. For this reaction again, we have products divided by reactants. We have our square here because we have a 2 for our product, the NO. We also have a square here because we have a 2 in our balance equation with the NOCl. So this would be our equilibrium constant expression for this reaction. In this reaction, the physical states of the materials are gas, gas, and gas. Gases and aqueous materials stay in the equilibrium constant expression because gases and aqueous materials have the ability to get their concentrations altered or changed. This is another equilibrium reaction. Let's write the constant expression for this reaction. This reaction, again, once again, its products is our numerator, reactants are the denominator. The coefficients in the balance equation become exponents in our equilibrium constant expression. And in this case, because all the materials are, we have gas, we have gas, we have gas, all the materials stay in the expression, leaving us with this for our equilibrium constant expression for this particular reaction. Let's do another example of setting up an equilibrium constant expression. In this reaction, again, we have products divided by reactants. The copper in the liquid form here does not appear in our equilibrium constant expression because it's a liquid, and also the CuO solid does not appear in our constant expression because it's in a solid state. Only gases and aqueous materials are used, giving this for our equilibrium constant. We have one more reaction. Let's try this one, setting up the constant expression. We have once again products divided by reactants. And we have two materials. Our solid iron does not appear in the expression. The Fe3O4 solid also does not appear in the expression. So for this particular reaction, this would be the equilibrium constant expression based on the materials that we have that are gaseous that stay in the expression and the solids that drop out. Another key concept in equilibrium is something known as Le Chatelier's principle. Le Chatelier's principle essentially tells us if something is done to an equilibrium system to throw it a bit out of whack so that it's not at equilibrium any longer, the system is going to respond or shift in some direction to try to bring the reaction back to a state of equilibrium. For example, here's our reaction. We're going to add a large quantity of C. What this does is the concentration of C goes up. The reaction is now no longer at equilibrium because there's excess C present. The reaction wants to get rid of the excess C. It can do that by shifting to the right or driving the reaction in the right direction or forward direction. By going to the right, the amount of B goes up, the amount of Y goes down, the excess C that was present gets consumed by being turned into product, the amount of C comes back down, and the reaction returns to a state of equilibrium. So for this we would say by adding C, the reaction shifts to the right and responds to that change in an attempt by the reaction to return to a state of equilibrium. In our next example, what we're going to do to stress the system is cool it. Now the system's at equilibrium and we come along and we're going to cool it, which throws the system out of whack so it's no longer at equilibrium. The reaction is going to respond to try to return to a state of equilibrium. Now by cooling the system, essentially what we're doing is taking the heat and we're removing the heat. The reaction is going to respond to try to generate heat to replace the heat that was removed. To create more heat, the reaction would get driven in the forward direction in that compound C and Y turn into B and form additional heat by being driven in the forward direction. So in response to cooling the system, this reaction would shift to the right to try to generate more heat to replace the heat that's been removed from the reaction. In our next example, we're going to add a catalyst. Now a catalyst speeds up a chemical reaction. In this circumstance, the catalyst does nothing to alter the equilibrium. All that happens is that we reach equilibrium quicker. It takes less time to reach the state of equilibrium, so there's no need for the reaction to respond and shift either left or right to return to equilibrium in this circumstance. We're now going to increase the pressure on the system. Now for this one, we have to examine the reaction and look at the materials that are gaseous. Only gaseous materials are influenced by a change in pressure. If we look at the reaction, we can see that on the reactant side, there are two particles or pieces that are gaseous. On the product side, there are three particles or pieces that are gaseous. Now what we've done is we've increased the pressure. So the system wants to respond to try to do something to make the pressure go back down and relieve the excess pressure, increase in pressure that's been added to this system. To relieve pressure, the reaction wants to shift to the side that has fewer particles. Fewer gaseous particles means less pressure. So in this case, to make the pressure come back down, the reaction is going to shift left, because by shifting to the left, we have three pieces turning into two, and that will allow the pressure to come back down and the system reaches equilibrium once again. In the last example, we're going to remove B from the system. If we take B and take it away, the reaction wants to respond to replace the B that's been removed. To generate more B, the reaction has to go to the right. C and Y get converted into B. So in response to this alteration to come back to equilibrium, we would say that the system would shift right to generate more B.